So now we're going to be looking at net torque and rotational inertia. Or in this case, a lot of these problems, they will call it moment of inertia. That's a more traditional terminology to use. But it means the same thing as rotational inertia. So those two are the same terms. So a flywheel, I equals 50 kilogram meter square, starting from rest, acquires an angular velocity of 200 radians per second, while the subject is a constant torque from a motor for 5 seconds. What is the angular acceleration? Okay, so the torque, so this is about angular acceleration. It's the change in angular velocity over time. That's what they're giving us here. Because it starts from rest and it ends at this. So we know that the change in angular velocity is 200 radians per second. And then it took 5 seconds to do that. And so that's 40 radians per second squared. What is the magnitude of the torque? Well, the torque is equal to I times alpha. That's what we're going to do for the net torque. And so that's equal to 50 times 40. And that's 2,000 Newton meters, which is the units of torque. A constant torque is applied to a rigid body whose moment of inertia is 4 around the axis of rotation. If the wheel starts from rest and attains an angular velocity of 20 radians per second, what is the applied torque? Again, the torque is going to equal I alpha on this problem. And I know what I is, so I need to figure out alpha. Alpha is the change in the angular velocity. It goes from rest to 20. So that's 20 divided by 10, or that's 2 radians per second squared. And so the torque's going to be this 4 times 2, which is 8 Newton meters. A torque of 50 Newton meters is applied to a grinding wheel. I is equal to 20 for 20 seconds. If it starts from rest, what is the angular velocity of the grinding wheel after the torque is removed? So torque's equal to I alpha, and this time they give us the torque and we can solve for the angular acceleration, right? Because they tell you it's 50 and the I is 20, and so that's 2.5 radians per second squared. But knowing alpha, I can figure out the angular velocity. So it does it for 20 seconds. So the angular velocity, remember the angular acceleration is the change in angular velocity per time. So, or in other words, the change in the angular velocity is angular acceleration times time, and that's 2.5 radians per second squared times 20 seconds, and so that's 50 radians per second. So that's the change, and because it starts at rest, that's the final angular velocity. Through what angle does the wheel move while the torque is applied? Here I'm going to have to use my kinematic equations. So its initial angular velocity was 0. Its angular acceleration we calculated was 50 radians per second. Actually, no, the angular was 2.5. Sorry, misread. Times 20 squared. 20 seconds squared. So that's 400, 200. 200 times 2.5 is 500. 500 radians. A pulley of moment of inertia 2 kilogram meter squared is mounted. So moment of inertia, this is the I. I is equal to this. On the wall shown as the following figure. Light strings are wrapped around 2 circumferences of the pulley and the weights are attached. What are A, the angular acceleration of the pulley, and B, the linear acceleration of the following weights? Assume the following data. R1 is 50 centimeters, R2 is 20 centimeters, M1 is 1 kilogram. So I want to do a free body diagram on both the pulley and this thing. So this is M1G down here, and this we're going to call T1, the tension here. And this, on this pulley, I have T1 acting here, and here I have T2 acting here. And on this free body diagram, I have M2G acting down and T2 pulling up. This is like the basics. The ropes are always pulling on the object, and they're equal and opposite if it's the same string. See, these two strings are different, so that's why the tensions are different. Okay, and then I want to calculate, so what I want to find is the angular acceleration of the pulley. So what I want to do is I want to do the net sort of equation. Well, actually, technically on this pulley, see how they're both pulling down? there actually has to be a restoring a normal force on the hinge. We'll call this the normal force to balance out these things. Otherwise, the pulley would be accelerating downward. But this force is not going to affect the net torque. Okay. So when I look at the net torque equation for this guy, for example, well, first let's get a sense of like which way it's going to accelerate. Like in general, everything is going to accelerate this way because the mass M2 of 2 kilograms. Well, I don't know. Let me see. And the pulley weights are attached. You don't actually know. So let's just establish direction. So let's just say this is the positive direction. This is the negative direction. Okay. And so if I'm going to say this is positive direction, I'm going to say this is the positive acceleration, and this is also positive acceleration for this guy. Because if I'm going to say that this direction is rotating positive, that means falling is positive acceleration and moving up is positive acceleration. Like that whole motion is positive. Okay. So the net torque that I would have for the pulley is T1 is acting at R1 at a distance R1. So, and that R vector, you see this R vector is already perpendicular. So I would just take R1 times T1 to get the torque. And that one's positive because this T1 is causing a rotation counterclockwise. Whereas this one is pulling clockwise, so this is a minus R2 T2, and that's equal to I alpha. Okay, so if I know the tensions, I can calculate what alpha, because I know I. Right? I know R1, R2, I need to know the tension. So then I'm going to look at the free body diagrams for these guys. Okay? This one, the net force is downward for M1. So I'm going to say it's M1G minus T1 has to equal mass times acceleration, which is M1 times A. Okay? And then finally, for T2, I'm going to do the upward force T2 minus M2G. It's also equal to mass times acceleration. In this case, it's M2 times A. Okay. Now, so the problem right now is the last piece of that's missing is, so if I list out my unknowns, I don't know T1, T2, alpha, or A. Those are my unknowns. And I only have 3 equations here. So the last thing is how alpha and A are related, because there's a relation between the tangential acceleration and the acceleration that we would see here. And in general, I would say that the tangential acceleration, let me think for, like, are these A's the same? No, these are 2 different ropes, so this A is actually a little bit different. This is A2 and this is A1. They're actually not going to move at the same angular velocity because they're at different distances. So what I have to do, so this is A1. So technically I have 2 different. What I need to do is relate this linear acceleration here with the angular acceleration. And if you remember, alpha is equal to, or alpha R is equal to A. Okay. So this one's going to be M1 and A1 is going to be the angular acceleration times this radius. So it's going to be alpha times R1. And this one's going to be M2 times alpha times R2. Okay. And now I have like this equation. What I want to do is I want to replace T1 and T2 and solve for alpha. Okay. So this equation I can rewrite as T1 is equal to M1G minus M1 alpha R1. And this equation becomes T2 is equal to M2G plus M2 alpha R2. And I'm going to plug both of these into this equation. So my net torque is going to be R1 times T1, which is M1G minus M1 alpha R, R1, minus R2 times M2G plus M2 alpha R2. That has to equal I alpha. So now I need to group all the alphas together and solve for alpha. Right? So I'm going to distribute R1 here. This is going to be M1 R1G. This one I'm going to move to the other side, so I'm not going to worry about this. Is minus M2 R2G is equal to I alpha. And then this term I'm going to bring over here. It's plus M1 alpha R1 squared. And then this is a negative here, and I'm going to bring it to the other side, make it positive, plus M2 alpha R2 squared. And now I can factor out an alpha. and I'd have I plus m1 r1 squared plus m2 r2 squared. And so the alpha is equal to this m1 r1g minus m2 r2g over I plus m1 r1 squared plus m2 r2 squared. And I know all of these values, right? So I can just compute them. M1 is 1, R1 is 50. And you can actually technically leave these in centimeters. You could put them in the meters, but the units will actually all cancel. So R1 times 9.8 minus 2 times R2 times 9.8 divided by I, which is 2, plus m1 r1 squared, which is actually I would put them all in the meters. Let me just write it all out. That I'm going to do 1 times 0.5 times 9.8 minus 2 times 0.2 times 9.8 divided by 2, because this one's actually in meters squared. I didn't think about this one's in meters squared. So plus m1, which is 1 times 0.5 squared plus 2 times 0.2 squared. So this is what I'm computing into my calculator. Get 0.42 radians per second squared. Okay, and then what is the linear acceleration of the weights? Well, A1 is going to be alpha times R1. So that's going to be 0.42 times 20 centimeters, or 0.2 meters. So times that times 0.2 is 0.084 meters per second squared. And then A2 is going to be alpha R2, and that's going to be 0.42 times 0. Oh, actually, sorry, I messed this up. This is this is A2, this is A1 here, because I messed up the units. So divide that by 2 times 0.5, and this one is 0.21 meters per second squared. So those are the two accelerations there. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.